Central Limit Theorem. Central Limit Theorem, one of the reasons that the normal random variable is so important is because of the Central Limit Theorem. Central Limit Theorem just says that for any large sample, for any random variable, large sample from any random variable, the sample mean, x bar, is approximately normal. And different books have different standards. The bigger the sample size is, the closer x bar is going to be to being normal. But our book uses the standard sample size is at least 30 or more than 30. So anyway, the formal statement: let x be a random variable with mean mu, standard deviation sigma. Then for sample size n greater than 30, whether or not x is normally distributed, the sample mean x bar is approximately normal with mean mu and standard deviation sigma over square root of n. Some books use n at least greater than or equal to 30. Our book uses n greater than 30. Generally, the bigger these numbers are, the closer the approximation will be. Then there's several special cases. The first special case, if it's not exactly a special case, but if the homework exam question states that x itself is normal, then the conclusion is true even for small samples. So if x itself is normal, even if you have a sample size 1, sample size 2, sample size 3, the sample mean is going to be normal. And usually, if that's the case, they'll say that in the homework exam question will state that x itself is normal. Special case 2, for sample size n, population proportion p, if np is at least 5 and n times 1 minus p is at least 5, then the binomial random variable x is approximately normal with mean n times p and standard deviation square root of n times p times quantity 1 minus p. And again, these numbers are a little bit arbitrary. Some books say that np has to be at least 10, n times 1 minus p has to be at least 10. Our book uses at least 5. Some books say strictly greater than 5. So but the bigger these numbers are, the closer the approximation is going to be. Okay, so this gives us a shortcut for computing binomial probabilities. That binomial probabilities can be rather involve quite a bit of computation. So so this gives us a shortcut. And again, these standards are arbitrary. Okay, so when using a continuous random variable, such as a normal random variable, to estimate a discrete random variable, such as a binomial, it is best to replace each whole number with an interval by adding or subtracting 0.5. This is called continuity correction. If you have a wide interval and if the sample is small compared to actually, if the sample is large, and if you have a large interval, then the continuity correction is not so important, and in those cases it's not always done. But especially if you have a small interval, like if you have a probability x equal 3, if you try to compute use the normal probability for probability x equal 3, you're going to get a probability of 0. It's not going to give you an accurate probability. But so if you make this into an interval by adding and subtracting 0.5, so you write this as the probability that x is between 2.5 and 3.5, and that way you replace x with an interval, and this will then, if you compute the z-scores, then you'll get an accurate estimate there. If you place probability x less than or equal to 3 with probability x is less than 3.5, because less than or equal to 3 means you're including 3. If you want to compute probability x is strictly less than 3, now you're not including 3, then you use probability x is strictly less than 2.5. So that's continuity correction, and it's not always done, but it does give more accurate answers. For sample size n and population proportion p, if n times p is at least 5, n times 1 minus p is at least 5, then sample proportion is approximately normal with mean p and standard deviation p times 1 minus square root of p times 1 minus p over n. And the sample proportion probabilities is actually related to binomials. You can switch from one to the other. P hat, if x is binomial, the sample proportion p hat is the binomial x divided by the sample size. So you can convert from a binomial to the sample proportion, and vice versa, sample proportion to binomial. That's just the binomial random variable divided by n. So the probabilities for p hat are related to those of the binomial. Usually continuity correction is not used for the sample proportion because usually the sample size, generally the sample sizes are big, and you're usually looking for intervals around p hat, not just exact p hat is exactly equal to a particular number. So it's usually not used for the sample proportion, although it would be more accurate to use continuity correction there. Okay, so again, it's the binomial divided by n. P has the binomial, so x divided by n. Or you can also write the binomial x is equal to n times p hat to convert from one to another. So you have to be a little bit careful. Both the binomial and the sample proportion, they both have a sample size n and a population proportion p. But the formulas are a little bit different. So for the binomial, the mean is n times p, whereas for the sample proportion p hat, the mean of p hat is equal to p without multiplying by n. And for the standard deviation, for the binomial, it's square root of n times p times q, or square root of n times p times 1 minus p. Whereas for the sample proportion, the standard deviation, square root of p times 1 minus p over n. So sometimes students get one confused with the other. So they're related and they're kind of similar, but they're different, and so it's easy to sort of get them mixed up. But be careful to use mean n times p if it's a binomial, mean is p if it's a sample proportion, and so forth. There's other approximations in addition to the central limit theorem. If n is large, for example, n greater than or equal to 100, and np is small, for example, np less than or equal to 10, then the binomial can be approximated with a Poisson random variable with mean mu equal n times p. And another approximation, you also use normal to approximate Poisson. If the mean is at least 10, and you're approximating normal with Poisson. And again, it's best to use continuity correction. It's not always done. If you have a wide interval, it's not so important, but it's more accurate to use continuity correction. These standards, n greater or equal to 100, n times p less than or equal to 10 are arbitrary. Np less than or equal to 10. Some books use p less than or equal to 0.01. Our book doesn't use that. Anyway, the standards are arbitrary. Not all texts use the same standards. Usually, a WebAssign will specify. Oops, it looks like I'm frozen here. I can't tell. On my screen, it looks like I'm frozen. I don't know about the record. There we go. Yeah, some books use p less than or equal to 0.01. Our book uses n to p less than or equal to 10, n greater than or equal to 100, and mu greater than or equal to 10, but not all books use the same standards. Usually WebAssign will specify when they want you to use approximations instead of the exact probabilities. Okay, so some examples. I'm calling this example 0. Suppose lung capacity has a population mean mu equal 3.1 liters with a population standard deviation sigma equals 0.5 liters. So suppose lung capacity was measured in sample n equal 1,000 patients. What is the probability the sample mean is less than 3 liters? So we're not told whether lung capacity is normal. We check that n is at least 30 or greater than 30, and yes, n is 1,000, it's more than 30. That means we can apply the Central Limit Theorem. And so on average, the mean of x bar, or the expected value of x bar, is the same as the population mean, which is mu, which is 3.1 liters. And the standard deviation of x bar is the original standard deviation divided by square root of n. So it's going to be 0.5 divided by square root of 1,000. And 0.5 divided by second square root 1,000. 0.0158. 158. 11388 liters. I'll store that in memory, my calculator. Okay, so then see, we can compute the z-scores. So we want the probability that x bar is less than 3, and make that into a z-score. Probability that z is less than 3 minus the mean, which is 3.1, divided by the standard deviation, which is 0.0158, 11388. Less than. Okay, so 3 minus 3.1, and then divide by second recall equals I get negative 6.32. Okay, so I'll just leave it at that. I mean, we would want to look at row 6.3, column 2, except that's our table doesn't go down, go up to 6.3. So it might be with technology you could get a probability there, but usually the tables don't go up to 6.3. If you look at our table here, the highest row number is 3.7, and the highest column is column 9. So 3.79 would be the highest z-score. That probability is 0.4999. So we have a one. We don't. If you're using the one-page z table, you can. You have to look up. It'll only have the positive z-scores, but the negative z-scores are the same. Going to have the same probabilities except for the sign because of symmetry. So this our table here gives a probability of 0.4999, or it's more than 0.49999. And so this piece here is, if you 0.5 minus that, 0.5 minus 0.49999 is going to be less than 0.0001. And this piece here, the z-score, probability z-score is less than negative 6.32, is going to be the same as this piece over here. It's going to be less than 0.0001, less than 0.0001. So it's going to be approximately 0.0000. It's going to be very close to 0. So in WebAssign, if they ask for 4 decimal digits, you can just type in 4 zeros after the decimal point. It's going to be very close to 0000. It's off the table. Okay. Okay, so that was example 0. We'll move on to example 1. And this time we have before we had a sample of size 1,000, and we're not assuming it's normal. But let's now assume that x is normal. With a normal random variable, you can still use the central limit theorem even for small sample sizes. So let's say let's assume x lung capacity is normal. Again, the population mean 3.1 liters. Population standard deviation 0.5 liters. Suppose the lung capacity was measured in a sample of n equal 4 patients. What is the probability of sample mean is less than 3 liters? So this is special case 1 of the central limit theorem. We can, even though the sample size is less than 30, we can still apply the central limit theorem. Again, the mean of x bar is the same as the population mean, which is 3.1 liters. Standard deviation of x bar, the original standard deviation divided by the square root of n. So it's 0.5 divided by square root of 4. That comes out to be 0.25 liters. And then we have the probability x bar is less than 3. Subtract the mean, divide by the standard deviation. We get the probability z is less than negative 0.40. So we want to look in row 0.4 and column 0 of the table, of the z-table. So 0.4 column 0, and that's 0.1554. So this is so I'll make a graph down here. So this this is not to scale, because I want it to want you to be able to see it. If I make it to scale, it's harder to see. So what's in the table is 0.1554, and this piece here is going to be 0.5 minus the table. Is 0.3446, and what we actually want is the probability that z is less than negative 0.4. But this is going to be the same as the left tail is the same as the right tail. So it's going to be our probability is 0.3446, or approximately 0.34. So that means there's a 34% chance that the mean lung capacity of a sample of 4 patients would be less than 3. And this would not be an unusual event. It would be unusual for the mean of a sample of 1,000 to be less than 3. That was very unusual, but the mean of a sample of 4 being less than 3, not so unusual. Okay, example 2. In 1876, Samuel Tilden lost the election for U.S. President to Rutherford B. Hayes in the Electoral College. Tilden actually received 51% of the, or majority of the popular vote. And that's happened in recent years too, at several occasions, where the person that the candidate that received the majority of the votes actually lost the vote in the Electoral College. That's just because of the way our voting system is set up. The states with smaller populations, which includes a lot of the rural states, have a disproportionate number of votes in the Electoral College, because they get each state gets 2 votes. Each state gets a minimum of three votes. They get two votes plus additional votes based on their population. So the two votes no matter what, and then additional votes, at least one more additional vote, but additional votes based on the population. So it's so the anyway, the some of the rural states that tend to vote Republican have a disproportionate amount of votes in the Electoral College. Okay, so anyway, so this 1876 election, Tilden got 51% of the vote, so P is 0.51. Suppose that a sample of 1,000 voters had been taken just prior to the election. What is the probability that less than 500 voters in the sample favored Tilden? So this is special case 2. This is actually a binomial. We're going to treat this as a binomial random variable, because what the probability that x is less than 500. So if we're computing probabilities about the proportion, then that would be related to binomial, but a little bit different. But this is here we want the probability x is less than 500. So that's not a proportion. That's a number. So that's a binomial random variable. So again, we want to check that n times p is at least 5. And 1,000 times 0.51 is 510. That's more than 5. That's yes. N times 1 minus p. Well, 1 minus p would be 1 minus 0.51 is 0.49. 1,000 times 0.49 is 490. That's also more than 5. So we can apply special case 2, and the mean of the binomial is n times p. 1,000 times 0.51, which is 510 voters. Standard deviation, square root of n times p times 1 minus p, 15.8 some voters. So maybe I'll store that in my calculator here. Second square root, so I don't have to type it in later. Times 0.51 times 0.49 equals. Okay, so I'm going to do this using continuity correction. It's maybe not be entirely necessary because this is a pretty large sample and it's a large interval. But if we do it using continuity correction, the probability of if x is normal, the probability of x exactly equaling 500 would be considered to be 0, but x is not normal, it's a binomial. So we want the probability x equal 500 to have a positive probability. So we're going to consider anything between 499.5 and 500.5 is equal to 500, and we want it to be less than 500. So we want the probability x is less than 499.5, And then we convert it into a z-score by subtracting the mean and dividing by the standard deviation. So the mean of the binomial for this binomial is 5 to 10, and the standard deviation is 15.80822.571. Okay, so 499.5 minus 510 equals, divide by second recall equals, I get negative 0.6642111164. So in order to use our z-table, I'm going to round this off. If you're using technology, you can keep all these digits and you'll get a more accurate answer. But I'll round this off here. And we want to look in row 0.6 and column 6 of the z-table. And so again, our text and also in the course files, we don't have the negative z-scores in here. So I'm gonna, this is not to scale, but so what's in the table is going to be the probabilities for the z-scores between 0 and 0.66, and then we can use the symmetry to get what we want. So 0.6 column 6, I get 0.2454. And if we do 0.5 minus that, that's going to be 0.2546. That's going to be the probability that z is more than 0.66, and that what we want is this piece over here is going to be have that same probability because of the symmetry of the bell curve. So so that's approximately 0.25. So there's a 25% chance that less than 500 voters in the sample would have favored Tilden. And if you used, if you did not use continuity correction, I think it would have been slightly different. But it probably would have been close because this is a pretty wide interval. So usually with the wide intervals, continuity correction doesn't make a lot of difference. Okay, example 3. This is actually the same example, except now I want to instead of computing the probability that a particular number of voters, I want to compute the probability that a proportion. So I want the probability that p hat is less than 0.5. So this is related to the binomial, but the mean and standard deviation are going to be different. Again, we checked that n times p is at least 5, yes. N times 1 minus p is at least 5, yes. And so we can apply special case 3. The mean of p hat is 0.51. That's the same as the population mean proportion, 0.51. And the standard deviation of p hat, 0.51 times 1 minus p, which is 0.49, divided by 1,000, square root of that. And that comes out to be 0.018082226. So let me put that into memory. Second square root 0.51 times 0.49 divided by 1,000 equals Okay, so now it's frozen. It looks like on my side it looks like I'm frozen, but I can't really tell. There. Now I'm not frozen. Okay, so we want the probability p hat is less than 0.5. So with the sample proportion, normally you don't use continuity correction, although it would be more accurate if you did. But usually the numbers are such that it's not going to make a big difference if you're using a sample proportion. So we want the probability p hat is less than 0.5, and we want to convert that into z-score. Probability of z is less than 0.5 minus the mean of p hat, which is 0.51, divided by the standard deviation of p hat, which is 0.0158082226. And then we'll get a z-score. And let's do that computation. 0.5 minus 0.51 equals, divided by, divided by second recall equals negative 0.632582061. Okay, so this is a little bit different than our z-score that we had before when we used continuity correction. If we had used continuity correction, we'd have a z less than negative 0.66, but now we have a z less than negative 0.63. So it's a little bit off, but again, usually continuity correction is not used with the sample proportion. So now we want to look at row 0.6, column 3 of the z-table, and 0.6, column 3, and I get 2357. 2357. I'll make a picture here. And again, you're using the symmetry. It's table 0.2357. And if we do 0.5 minus that, 0.2643. 0.2643, and this one's going to be the same. And this is actually what we want here, but that's going to be the 0.2643. So it's approximately 26%, but 26% chance of this happening. So before we got 25% chance, but this is a little bit off, but that's because we didn't use continuity correction. Okay, another example. A large country, the proportion of infants with HIV, P equal 0.008, and sample of N equal 2,000 such infants. The X represents the number with HIV. So X is binomial, N is 2,000, P is 0.008. Find the probability that 15 of the 2,000 infants have HIV. So the exact probability, this is binomial, and it's for this particular problem, binomial is not hard. Sometimes, depending on the problem, binomial can be rather involve a lot of computation, but this one is not too bad. Probability x equals 15, 2000 choose 15.008 to the 15.992 to the 2000 minus 15, which would be 1985, and that comes out to be 0.0996. If we estimate using Poisson probabilities, well, it doesn't meet the standards for our book. Different books have different standards. It doesn't meet the criterion for our textbook because, well, n is more than 100, so that's 2,000 more than 100. That's a yes. But n times p would be 1,000 times 0.08, which would be 2,000 times 0.008, which would be 16 infants, which is not less than 10. So that means Poisson probabilities might not be accurate. But actually, as it turns out, they're not too far off. If we plug into the Poisson formula, 16 to the 15 times e to the minus 16 over 15 factorial. This is the mean is 16. And x is 15, so we put in those numbers there. That comes out to be 0.0992. In WebAssign, if they ask you to use Poisson approximation, then you should use that, even whether or not it meets the standard here. According to the National Weather Service, an average of 17.8 hurricanes per decade strike continental United States. Assume that number of hurricanes follows a Poisson distribution. Find the probability of 16 hurricanes in the current decade. So if we're using the exact Poisson probabilities, plug into the formula, probability x equals 16. The mean is 17.8. You put that in here. Put x 16, put that in these two places here. That comes to about to be 0.0903. If we approximate with normal probabilities, check that the mean is at least 10, and that's a yes. So a normal probability should be reasonably accurate. The mean is 17.8. For Poisson, the standard deviation is the square root of the mean. So that's a special formula only for the Poisson. Square root of 17.8 comes out to be about 4.219 something. And then if we use continuity correction, probability x equals 16 will be a probability x of between 15.5 and 16.5. This one you almost have to use continuity correction because for a normal random variable, the probability of x exactly equals 16 is considered to be 0. So you need to have an interval in order to get a positive probability here. So we add and subtract 0.5 to the 16. So then make things into the z-scores by subtracting the mean divided by the standard deviation. This comes out to be negative 0.55. This was negative 0.31. Look up each of these numbers in the table and then subtract because we want the number in between. These are like signs, so if you have z between a negative and negative, you want to subtract the numbers in the table, and that gives an answer of 0.0871. So it's at least rounded to the nearest hundredth. It's going to be the same. So basically, we to one significant digit, we have the same. They both round to 0.09, approximately 0.09. So they're the same, except to the first significant digit at least, but they're maybe a little bit further off than we would like. Anyway, that concludes this presentation.